There we go. Thank you. So that's kind of interesting because some people can do it and some people cannot. If you are nearsighted, it actually helps because you can take off your glasses, assuming your two eyes are about the same prescription. You can take off your glasses and you can look at it up close. And when you look at something up close and you intentionally relax your eyes so they don't do the cross-eye thing, then you actually can see the depth, the 3D version of this particular picture. It's really kind of cool. All right, let's see. What time is it? 10 more seconds. So this is kind of fun stuff. The Design Hub is actually doing quite a bit of work this semester. There's only one person assigned to the Molecules project. If you're interested in learning how to use a game engine to help younger students, like elementary school students, to learn about chemistry, how to put molecules together and stuff like that, the Design Hub certainly has openings in spring 2022. So if you're interested, you might want to contact Randy Schuster. Professor Schuster is the person who's leading the Design Hub for projects like these. So I personally kind of like to use just a flat monitor and be able to let people have depth perception, because otherwise it's pretty hard to actually see in 3D what this molecule looks like. Alright, so it is time to get started. Alright, so fun stuff is just this, and then the homework assignment is assigned, so I just did. Okay, I forgot about this entirely over the weekend, so I just assigned the Dijkstra's algorithm lab or homework assignment. It's basically just a trace of a graph. You should be able to access it in Canvas already. So there you have it. Alright, so we have some questions to ponder. Not something that I would ask you guys to prove in this class, but I would like you guys to kind of think about it. So when you look at Dijkstra's algorithm and when you look at the A-star algorithm, I would start with Dijkstra's algorithm first because that really is the simpler of the two. You might want to kind of think about this a little bit. How do we know these algorithms are correct? And how do we define the correctness of an algorithm to begin with? So kind of think about that a little bit. How do we prove the correctness of an algorithm? So where do we start? What kind of techniques do we use? Now we have two really powerful techniques of proofs that are particularly useful for this sort of thing. One is proof by induction and the other one is proof by contradiction. So both of these are very useful, general proof techniques. But when you're trying to prove the correctness of an algorithm, both of these are actually very, very useful. And I can give you a clue in terms of how you can use induction. So induction and recursion are very related. But we also know that any loop, okay, any iteration, any for loop, while loop, can be turned into recursion pretty easily too. So what you're looking at here is to look at a loop as if it is a recursion, even though it's not. And then you're using induction. Basically, you have a base case. The base case is the very, very last iteration. And then you're going to back up, or you can look at the base case as the first iteration and then the next iteration. So you're using proof by induction to basically say, okay, if we make this assumption, can we prove that the next iteration would also have the same property? So that's kind of the direction you can head out with. Don't spend too much time, just kind of put this at the back of your brain, and just think about it a little bit when you have time. But those are the sort of things that I think will help you understand the algorithm better when you spend more time to kind of ponder upon these things. So without any questions in the text channel, and I don't see any, I'm going to get started with the trace of the graph that we talked about last Wednesday. There are a few links in the text channel. I think you guys really might want to go there. One link is the A-star algorithm itself, which is in the module. So you might want to open it up as a separate window. Another one is a spreadsheet. So you might want to open that, using another window. It depends on how big of a screen you have and how small of text you can read. Because one is going to be kind of like the table, because I'm not going to use Joplin to track this one because it's just too many columns to track. It's not very feasible. You can use two monitors for sure. I use a 4K monitor, and that works really well too. Otherwise, you can use multiple windows and just kind of use Alt Tab to switch between the windows. It's not going to be as good, but short of having the real estate, that would be the next thing to do. Monitors are not really super expensive. That it's not that anymore. So I think just look at it as an investment. I mean, it's much less expensive compared to some textbooks in some classes. So now that this class has no textbooks, right? You're saving all that money, and hopefully you can find a second monitor to hook up to your computer. I think that's going to be very helpful. Alrighty. So we got Armand still typing. Alright. Alright, so that's what we are going to do today. Is really the first thing is to trace the A-star algorithm, because when we trace an algorithm, I think we'll get a better understanding of how it works, and also maybe even some insight of how we can prove the algorithm is correct. Alright, so we are going to get started. Alright, so I'm going to switch to my browser. Oh, very good. Okay, I can see a bunch of people are already at the spreadsheet that I created just for tracing the algorithm for today's demonstration. And I have the graph showing on my side. Okay, so I just opened it up as a PDF. By the way, the PDF is from the text channel from last Wednesday. So if you prefer to use a PDF, go ahead and go back to that channel, grab the PDF and open it up. And we are also going to need the algorithm itself. So I got it over here, but you might want to peel it off on the side, so that way you can focus on the trace of the table itself when I'm referring to the algorithm. So that's also what I would do. I'm just going to peel off this tab here to the side, so I can now see the graph, I can see the algorithm, and I can also see the spreadsheet at the same time. So do we have any questions before we get started here? Okay, no questions. Alright. Can I explain one line one more time? Alright, so let's take a look. Yes, so A star starts with one single start vertex, and there are ways to convert multiple start vertex problem into a single start vertex. The easiest solution is to have zero distance edges leading from a virtual start vertex to all the... Oh, okay, I see. From the A-star algorithm. Not really sure whether that's gonna work or not. I think it's from one single start vertex, which is the start vertex that the algorithm knows about, and then from that one we can use zero cost or zero distance edges to go to the other quote-unquote start vertices. So yes, so that would be one way to emulate the effect of having multiple start vertices. But the problem is the solution will only choose one of them. We'll never find the solutions. We will never find the shortest path from every single start vertex to a destination vertex. So that part of the algorithm is going to stay the same. So so the zero transition may be able to help identify there are multiple places that we can start, but it will still identify only one shortest path from one of them to the destination. That will still be the limitation of the algorithm. So we can't quite do the same thing as Dijkstra's algorithm in this case. Alright, so let's go ahead and get started here. So in the algorithm, we have G. So G is the graph. I'm gonna show the graph here. So it has all the set of all the vertices. Basically A, B, C, D, E as a set is V, and then all the edges are the same as the example that we used for Dijkstra's algorithm last week. We have the same distances, so I have not changed the distances at all compared to the problem for Dijkstra's algorithm. So one thing I did add would be the H function. It is not the complete H function, because in this case I only demonstrate the heuristic from a vertex to vertex E, because vertex E is the destination vertex. So that's why H is actually just a partial set in this case, because H, generally speaking, is going to give you a number for each pair of vertices. In this case, this is basically a subset. I should probably make a notation here to say this is actually just a subset, but this is the subset that we actually need to use. The rest are really useless to us. And then we have S being A. Okay, so this is our start vertex, and then E is our destination vertex. That's basically X in the algorithm itself. And that's it. Okay, so I'm gonna put this back on the side so I can actually focus on the algorithm. Yeah, I'm just looking at my I'm looking at my PDF, and I think if I can get rid of the preview page tab, I might be able to. Well, barely. It doesn't quite fit entirely. I'm trying to fit it into over the spreadsheet, so that way I can shrink it a little bit and it's going to fit. But then the graph is going to be a little bit smaller than I would like it. Still works. Okay, so it's better than nothing. There we go. Alright, so what we'll do now is really just to get started with the algorithm. So the algorithm starts with for each v in lowercase v and uppercase v, do initialize it. Okay, so that's the initialization. The initialization basically has to do with the g function and the f function, and also the pref function, because we want to make the previous to be all undefined. Alright, so with the g function, except for the start vertex, everyone is going to have infinity. So A is the start vertex, so it's going to have a g value of 0, and then everything else is going to have infinity. Because remember, the g function, or the g value of a particular vertex, is the length of the known shortest path from the start vertex to that particular vertex. So A is a start vertex itself, so the length of the shortest path to itself is going to be a 0. So that part should be intuitive. But for all of the other vertices, we have not explored a single edge yet. So we're making the assumption that maybe those are not even reachable. Okay, so we put infinity here as the length of the shortest path from the start vertex, which is A in this case, to the other vertices. Now f, on the other hand, is basically g of the same vertex plus the heuristic of that vertex to the destination vertex. So in this case, if I go back here, let me see if I can make this always on top. So there should be a way to do that. Yep, there we go. Alright, so this is always on top, so this way when I click on the spreadsheet, this particular graph is not going to go away. Alright, so the f function is the g function plus the heuristic function from the vertex all the way to the destination. So our destination is E, so that means f of a is 0 plus the heuristic value of ae. So if you look up the graph, the heuristic function is right here. Ae has a value of 13. So 0 plus 13 is 13 itself. And then the rest are also just infinity. Remember, these are the g value plus the heuristic value. Since the g values are infinity already, doesn't really matter what you add to them, they'll always be infinity. And then the prefs are basically initialized to all unknowns. I'm not going to type out the entire word because that's going to take up too much space. So this is how we initialize everything in the algorithm. And after initialization, we are now moving on to the initialization of O. So the O set here is pretty easy because all we have to do is to put the start vertex into O before we get into the while loop. The start vertex in this case is vertex A, so I'm going to put vertex A into here. And that's it. That basically are all the initialization steps. So now we're getting into the while loop, and when we get into the while loop, the first thing we ask is, okay, let's check out all the vertices in set O and make sure that at least one of them has an f value that is less than g of the destination. The destination is e, so the g value of the destination is infinity, and then the f value of a is 13. 13 is less than infinity is true. Okay, so very good. Okay, we have found at least one element in O that satisfies the requirement that the vertex in O has an f value that is less than the g value of the destination vertex. So at least one vertex has to meet that requirement in order for us to continue with the loop body, and we found that the only element does meet that requirement. So it doesn't really need much explanation that this also is going to be the vertex that we choose from the set O, because there are no other alternatives. We don't really have anything to compete with vertex A. So once we did that, we have to take it away from the set O, and now we have to go to the inner loop, the for each loop. So we have to look at all the neighbors of A, in other words, every other vertex that is reachable by one single edge from A. There are two edges like that. A goes to B, A also goes to C, so we have two iterations in this case to consider. The first one is AB. Okay, so we say AB, so the variable V of the algorithm is vertex B in this case because we are considering the edge AB. And this time, unlike Dijkstra's algorithm, I use a temporary variable t to store the length of the path from the start vertex A through the vertex that we are now considering, which is vertex B, to the destination. So we are now considering, okay, let's check out from A to B and then just guess the rest of the way to E. What is the estimate of that path? So what we do is now we look at A to B has a distance of 1, and then we just use the heuristic from B to E to kind of guess how what is the length of the rest of that path. Alright, so we have some text messages. Yes, the guess is coming from the heuristic. So in the heuristic function, we have BE having a value of 12. So we have 1 plus 12, which is 13. So T is 13 in this case. So now what we do is we go back to the algorithm, and there's a conditional statement in the for loop that says if t is less than g of n, then blah blah blah. Okay, so we now want to look at g of n, and n is, oh, instead of v, I think we have n. Yeah, I chose the wrong name for the variable. Sorry about that. This is actually n, not v. No, the heuristic is given to you. So typically the heuristic will be something that's easily computable. So in the case of a map, it's going to be the distance of the straight line between 2 points. In the case of some optimization algorithm, maybe one step it has a value of 1, or something along that line. And yes, so it is a function. So in this case, okay, I arbitrarily chose well, I shouldn't say arbitrary, because I did choose certain values to try to trick the A star algorithm, but it is arbitrary from the perspective of it doesn't have a closed form equation of, oh, by the way, this is the universal way to compute the heuristic value between any two vertices. We don't have anything like that in this example. In this example, I hand-picked those heuristic value because I say, let's do something to try to trick the A star algorithm so that maybe it would not find the shortest path if I did these tricks here. But in general, in general, you would figure out a way to compute the heuristic in a very quick way, but it would still be informed enough that it would be better than Dijkstra's algorithm, which is uninformed. All right. So Amal is typing. AE heuristic is already the shortest. Yeah, so from the start point to the end vertex, that one doesn't really matter because the heuristic value from the start vertex all the way to the end doesn't really give us any. It's useless because after all, what we're really trying to do is to say, okay, which one should we choose now? Should we choose vertex B or vertex C, right? So the heuristic from A all the way to E is not really giving us any useful information as to which way we should go when we have two vertices to proceed at that point. So yeah, so it's at this point, the heuristic value of AE is I can make it anything, and it's not going to change how the algorithm works. Right. Okay. So so this is 13, and we want to find out what is the value of what is the value of g of n, which is g of b in this case. So g of b is still infinity. So t is 13. We are asking, is 13 less than infinity? The answer is yes. So when the answer is yes, we go into the then branch of the conditional statement. So the first thing we do is we add b to the set O. So now this has vertex b in it. So A is already out of the set O because of the statement outside of the for each loop. And then the second item is we're going to change pref. So pref of B is going to be A. So this is our way of remembering, okay? In order to get to vertex B, we came from vertex A, okay? We think this is the shortest path, at least at this point. And then the third thing is to change g of n. So g of n is g of b. It is now changed to the value of t, which is 13. And then we also have to update f of b, which is 13 plus the heuristic value from b to e. So when you look it up, b to e is 12. Oh, okay, wait, hold on a second. I just got it wrong. Yeah, I just got it wrong here. So the t value, okay, erase all of that, okay? The t value does not use the heuristic. It really is just the g value of vertex n, the g value of c plus the distance of the edge AB in this case. So it would be 0 plus 1, which is just 1. So the g value would be 1. And then the f value is going to be 1 plus the h value between b and e, and then the h value between b and e is 12. So this is the only one that gets a value of 13. Sorry about that. I totally did the wrong thing in order when I was computing t. So are we doing okay so far? Let me show you. Oh, yeah. Okay. Alright, cool. Alright, so now we can explore the other edge. So this is the edge AC. Okay, so we change only n to c because now we're considering the edge AC. So we compute the value of t again, which is the g value of a, which is 0, plus the distance of the edge AC. The edge AC has a distance of 8 in this case. 0 plus 8 is just 8 itself. Now we want to compare 8 with the g value of n, which is the g value of c. The g value of c is infinity. 8 is less than infinity, so now we are going to go through the then statement again by adding c into the set O. And then the next thing we do is to change the previous of c to a. There we go. And then the next thing is to update the g value of c, and that's going to be 8. And then we also want to update the f value of c, so that's going to be 8 plus the heuristic value from c to e. The heuristic value of c to e is a gross over underestimate. It is estimated to be 0. So 8 plus 0 is just 8. So I hope you guys are starting to see why I said what I said earlier, which is I'm making up these heuristic value to try to trick the A-star algorithm to do the wrong thing, because I'm saying hey, the shortest path is actually the other way. Try the other way. I'm trying to trick the A-star algorithm not to find the shortest path. But as we'll find out, it's going to find the shortest path. It just has to explore a few additional edges, than otherwise, but it will still find it. Alright, so we are now done with the for each loop, and because there are only 2 outgoing edges from A to B, one to B and one to C, so now we are out of the for each loop and back to the while loop. So when we get back to the while loop, the very first thing we ask is, out of all the vertices in O, is there at least one where its f value is less than the g value of the destination itself? That's a pretty easy question to answer, because the destination still has a g value of infinity. Okay, and if you think about it, by the time a vertex is in O, its f value is not going to be infinity, because the only reason why a vertex would appear in the set O is because its g and f values just got updated. And when you look at how the g and f values got updated, it's because the g value is now non-infinity. And that's the reason why we kind of know that if the g value of the destination is still infinity and O is non-empty, we are pretty sure that all of these, every single one vertex in the set O is going to have the f value being less than the g value of the destination. Is that reasoning okay? Do you guys kind of understand what I was saying? Okay, all right. So what I said, really has to do with analyzing the algorithm itself. Okay, we're asking, how do we get a vertex into the set O? Okay, what can lead to a vertex appearing in the set O? And every single update, okay, that will add a vertex into the set O has something to do with the g value getting assigned something that is not infinity. So that's important. Okay, that is really important, because we want to understand how the structure of the code is leading to certain properties that we are starting to I wouldn't say understand, that we are starting to notice. Okay, we're starting to observe those properties. But then when we get to the next statement, which is let C of C in O such that for all W in O, f of C is less than or equal to f of W. So now that we have 2 elements to consider, we want to pick one of them, and the one that we are picking is the one that has the least f value. So we are looking into f of B. So f of B is 13, and we're looking at f of C, which is 8. So we are now picking C as the next vertex to expand. So lowercase c is a variable, uppercase C is the value in that variable. Okay, so that's why we have lowercase c, which is from the algorithm itself, and then we have uppercase C here, which is the name of the vertex over here. So we're going to do the same thing, okay? Get C out of the set O. So now set O only has B as the only remaining element. And then we're going to go expand C and basically follow all the outgoing edges from C and see, what we can find here. So C is quite busy because it has 3 outgoing edges. One is going back to A, one goes to D, and one goes to E. So we're going to explore all 3 of them. And we'll start with CA here. It doesn't really matter, okay? When you're dealing with the for each loop, which one you explore first really should not make much difference. All right, so we are looking at CA first. All right, so what is T? T is G of C plus the distance of CA. What is G of C? G of C is 8. And then what is the distance of CA? That is a 0. So now we know T is going to be just 8. And the question is, are we finding potentially a shorter path from the start vertex to vertex A? That's the question, okay? So we are now comparing T with G of A. G of A is a 0. T is an 8. Nope, I'm pretty sure 8 is not less than 0. So, okay, well, we are not going to get into the then branch this time. So now we look at another outgoing edge from C, and this one is from C to D, and we want to compute T again. So once again, we look up G of C, which is 8, and then we add to it the distance of the edge CD. So CD has a distance of 2. 8 plus 2 is 10. And now we ask, is 10 less than the length of the shortest known path at this point to vertex D from the start vertex? That would be G of D, and G of D is infinity. Okay, well, 10 is less than infinity. Yeah, that sounds pretty true. Okay, so we need to add vertex D to the set. So now the set has B and D in it. We are going to go update the previous of vertex D so that it is now C. So we look up this column, update this to vertex C, and then we are going to change the G and the F values. The G value is just going to be whatever T is. So in this case, it is 10. And then the F value is whatever the G value is, and then you have to add the heuristic value from vertex D in this case to the destination. So in that case, we have DE having an H value of 4, so we have 10 plus 4, which is 14. Now we have one more outgoing edge from C, which is from C to E. There we go. And even though E is our destination vertex, it has no special meaning. It is not treated any differently at this part of the algorithm. In fact, at all parts of the algorithm, we never say, hey, this is the destination vertex, let's do something differently about it. Nope, we don't notice at all that this is the destination vertex. We don't do anything special in this algorithm, even though this is the destination vertex. So we're going to do exactly the same thing. Let's first compute T, which is G of C in this case, plus the distance of the edge CE. So G of C is 8, and then the distance between CE is 10, so we have 8 plus 10, which is 18. And now we ask the question, have we found a shorter path from the start vertex through C and E to the destination vertex? So we have to compare the 18 to the G value of E itself, and the answer is yep, I think 18 is less than infinity. So we have found a shorter path from the start vertex through vertex E to the destination, which is also vertex E. But once again, we are not giving the destination vertex any special treatment. We go through the same logic as all other vertices. So what do? We add E to the set O. Okay, B, D, and E. And then we update the destination, the previous of E, so that it is we make a note and say, hey, if we want to get to E, we can come from C, and then when we get to C, it says we can come from A. So technically speaking, we have found a path from the start vertex to the destination at this point, but we don't know whether it is the shortest or not. Okay, so when we get back to the while loop, I'll explain why we know we have not. We cannot confirm that we have found the shortest path. But at this point, we're going to finish up the then statement of the conditional statement. So the other two things we need to do is to update the G value. The G value is simply whatever the T is. Okay, so it's 18 in this case. And then we also have to update the F value, which is the G value plus the heuristic value to the destination vertex. Once again, if we just look it up like every other vertex. Okay, so we look up the table here, and it says h of E, okay, the heuristic value from E to E is 0. Oh, okay, we add 0 to the G value, which is 18, so it is actually just 18 here. And you can see that, we don't really care that we just found a path to the destination vertex. There's no special consideration. Alright, so we are now done with the for each loop, which means we're now going back all the way to the while statement. The while statement is looking at these three vertices, and it's asking, is the F value of at least one of these three vertices less than the G value of the destination vertex? So, well, let's go check it out, right? So at the F value of B is 13. The G value of the destination is 18. It's no longer infinity, but 13 is still less than 18. So we have at least one element in O where the requirement is satisfied. It has an F value that is less than the G value of the destination. Alright, so mechanically it's pretty easy, right? Mechanically we are just kind of following the meaning of the set operation, following the meaning of the less than operator and stuff like that. But semantically, what does that mean? Why is this significant? What does it mean, when that condition turns out to be true? So that would be the question that you need to ask yourself. It's not really just mechanically how we do this, but in terms of the meaning of the algorithm, why is it significant? Okay, so the significance of this is basically saying, look at this. Okay, this is an estimate. Okay, this is just an estimate of a path from the start vertex through vertex B to the destination vertex, and we are estimating. Okay, I know this is probably a underestimate. At best it is an exact value, but we know this cannot be an overestimate. In other words, the actual shortest path from the start vertex through vertex B to the destination cannot be let me think cannot be less than 13. Okay, so there's a chance that maybe there is a path with exactly this value through vertex B to the destination. And what we also know is the shortest path, the length of the known shortest path at this point to the destination is 18. So there is a chance that we can find the shortest path through vertex B. And the same thing can be said about vertex C, because it looks even more promising that we can find a shorter path through vertex B. And don't forget vertex D, it also satisfies that requirement. So I heard a few dings from the text channel. Oh, okay, that's good. Yep, exactly. Because if the heuristic is not admissible, which means it can potentially be an overestimate, then the algorithm can conclude too early without actually finding the shortest path. That is why we need the heuristic not to overestimate. It can underestimate by a great deal. Okay, put a 0 there when it's supposed to be 600. It's okay, you can trick the algorithm to go through a few more vertices, but it will still find the shortest path. But if you put in a heuristic value that is an overestimate that is greater than the length of the actual shortest path from a vertex to the destination vertex, then the algorithm can be incorrect in that case. It will conclude, saying that, yeah, look at this, I found the shortest path, when it is really not the shortest path. So this part is kind of important. All right, so what we are going to do next is to say, okay, but who's going to be in the variable c in the next iteration? Well, that's pretty easy. We just find the one that has the least f value of all the vertices in set O at this point. So we got B, we got D, we got E, and somehow C is not in it because C is already taken out when we explore other things. So we only have B, D, and E to consider in this case. B has a h value of 13. D has a h value of, a f value of 14. So, and then E has a f value of 18. So of the three, we're going to choose the one that is the least. So that it would be vertex B. So vertex B is now becoming the value of variable C in this case. And we're going to have to look at all the outgoing edges from vertex B now. All right, so vertex B goes to vertex C, it goes to vertex D, so it has two outgoing edges. So we'll explore these two, one by one. Okay, we're going to explore BD first. And the way we compute local variable t is kind of the same way as you always. And I can shrink these columns a little bit because they really don't need to take up that much space. There we go. And now I can move the graph over a little bit here, and you can now see the entire h function. Well, at least all the values that we care about. Alright, so what is g of b? G of b is 1. What is the distance between b and d? That would be 10. So we have 11 as the value of t, and now we want to compare that to g of d. G of d is 10, and this is 11. So we did not find a shorter path from the start vertex to vertex D in this case. Alright, fine. Let's consider vertex C. We're considering the other outgoing edge from B, which is BC in this case. And we are going to compute T using G of B plus the distance of the edge BC. G of B is just 1, and then the edge from B to C has a distance of 6. 1 plus 6 is 7. And now we're going to compare this 7 with G of C. G of C is representing the length of the shortest known path up to this point from the start vertex to vertex C. This 7 here is representing the length of an alternative path from the start vertex to vertex C. So as we can see here, we have just found a shorter path. Okay, now I didn't quite say the shortest path, I just said a shorter path from the start vertex to vertex C. So we are now going into the then portion, and guess what? We're gonna put C back into the set. So, oh, I forgot to get B out of the set first. Sorry. So that's a okay. What is going on? Alright, so let's do this. I just forgot to take B out of the set O. Interesting, it's not letting me type. Alright, so let me move this out for a moment, and I'm gonna refresh. Alright, and we want to change this. Okay, now it's good. So we only have D and E left in the set at that point because we take B out of the set. So when we found that, hey, there's a shorter path through to vertex C, we have to add C back into the set. So C, D, E at this point. And then the second thing we do is to update the previous. Yep, so we update the previous of C, so it is now B and not A. So we go here and we change it from A to B. And then we update the G value and also the F value. So right here we update the G value from 8 to 7. And then we also have to update the F value. And let me pull the heuristic value back into view so that you guys can see it. Alright, so from vertex C to vertex E, the heuristic value is 0. Okay, so it's the same as the G value, which is also 7 in this case. And there's some text traffic. Oh, okay, there we go. Okay, I just brought the graph back into view. Alright, so that's the update for vertex C. And let's see, do we have any other edges? Nope. Because vertex B just has 2 outgoing edges, and we have already considered both of them. So the for each loop is now done. We are now back to the while loop. So once again, we ask, do we have at least one of these 3? Okay, can we confirm that at least one of these 3 has an F value that is less than the G value of the destination vertex? So we are now focusing on just the F values. The F value of C is 7, and that is already less than the G value of the destination, which is 18. So we don't have to look at the other 2. I mean, once we confirm that at least one of them, has that property, we're good. Okay, we can now go into the body of the while loop. So the next question is, of these 3, which one are we going to choose? Well, that's based on the F value of C, D, and E. So we can see one has an F value of 7, one has an F value of 14, and one has the F value of 18. So we just pick the one that is the smallest, which is vertex C again. So now the variable C has a value of vertex C, and this time I remember to take it out of set O. And here we go again. We're back to vertex C, and we go like, okay, what are the outgoing edges from C? Well, the same 3, right? A, D, and E. So we already know that part. So we can say, yeah, we're gonna have to look at all 3 edges again. So this is one thing that you might notice. It's already different between the A-star algorithm versus Dijkstra's algorithm. Dijkstra's algorithm guarantees to only look at an edge once, and only up to once, okay, I should say, because some of the edges it might not even consider. But the A-star algorithm can go back to a vertex and then look at all the outgoing edges from that vertex again. Okay, so from that perspective, the A-star algorithm can certainly be quite inefficient, okay, because you can basically hand pick and hand design your heuristic value to make it work, okay, to make A-star algorithm work. But it would not be incorrect, okay, it will still find the right answer. It's just that it's gonna take a little bit longer. Alright, so let's take a look at CA as an edge, and we'll look at the T value, which is the G value of C plus the distance of CA. The distance of CA is 0, but in this case the G value of C is 7, so we have a T, the local variable T has a value of 7, and then we compare this with the G value of vertex A. The G value of vertex A is a 0. So we are asking, hey, is 7 less than 0? The answer is no. Okay, well, we are not getting into the then branch of the conditional statement. So now we look at D. C has a G value of 7, and then the edge, or the distance of the edge CD, has a distance of 2. So we now have 7 plus 2, which is 9. Okay, so we say, hey, we just found a path from the start vertex to vertex D, and it has a length of 9. Did we just find something shorter than what we had before? The answer is, oh yeah, because the previous one has a length of 10, and we just found one that has a length of 9. So we did find a shorter path. Okay, make sure that D is in the set O. Well, see, it's already there, okay, but I'm just gonna re-emphasize that we have to update set O, okay, because we are supposed to add vertex D to the set. We just cannot have duplicate elements, so it's doing an update. And then we update the previous. So we look up D and say your previous is now C, and it was C already. And then we update the G value and the F value. So in this case, the G value is 9, and then the F value is going to be 9 plus the heuristic value from D to E, and the heuristic value from D to E is 4, so 9 plus 4 is 13. And then we look at the next outgoing edge from C. It is going to E directly, so we are looking at this particular edge here. And then we ask, did we find a shorter path? The answer is, yeah, I think we found a shorter path, because G of C is 7 at this point, and then the distance of the edge CE is 10. So we found a path with a length of 7 plus 10, which is 17. So now the question is 17 shorter than the length of the path that we have found up to this point? And the length of the path that we have found up to this point has a length of 18. We just found another path with a length of 17. So yeah, so we just found a shorter path. Cool. So let's add E back into the set O. Okay, it's already there. Okay, but it's okay. We can still just say that we updated. And then we're going to go to the previous. We update the previous of E to be C again. Okay, but it's already C. It's okay. So it's not technically changing anything, but it's still an update. But the most important part is we are now also updating the G value to be 17, and the F value is also 17 in this case, because the H value from E to E is guaranteed to be 0 because it cannot overestimate. So there we go. So now we are out of the for each loop and back to the while loop. And once again, we ask the question, of the two elements in O, does at least one of them have a F value that is less than the G value of the destination, which is E? So we focus on the F value. The F value of D is 13, and then the G value of E is not 18 anymore, but it's not really that much better than before. It's 17. The answer is yeah, so 13 is still less than 17, so it is still possible at this point to find a shorter path than the one that we have found. So if somebody is wondering, okay, and it would be a very good sign if you guys are wondering about this, is but are we guaranteed that we can still find a shorter path at this point? The answer is no. Okay, there's no guarantee. Okay, it's just that there's a chance, there's a possibility that we can find a shorter path from the start vertex to the destination vertex. This thing here, remember, is an underestimate. Okay, can be way under. Okay, so there's no actual guarantee at this point. Now if you look at this part here, then your eyeball algorithm will confirm and go like, yeah, there's a shorter path. But if you cannot actually see the entire graph and you can only work with what you have at this point in the algorithm, the answer is no. There's no guarantee that there actually is a shorter path, but there's the possibility that a shorter path does exist. So we have to keep going until that possibility is gone. Okay, then we can say, okay, it's time to conclude, because we know there cannot be a shorter path at this point of time. But at this point, there still can be a shorter path. All right. So now we get back into the algorithm, because the F value of D is less than the G value of E. Of these two, let's pick the one that has the least F value. So the F value of D is 13. The F value of E is 17. So we're going to pick D. So D is going to be here. And then we take it out of the set O. And now we consider all the outgoing edges of D. There's only one, which is DE. So now we say, well, there's only one. We are going to E from D. And now we ask, what is the length of the path going from D to E? So we look up the G value of D first. It is 9. And then we look up the distance of the edge from D to E, and that is 4. 9 plus 4 is 13, so we put 13 here as the value of t, which is basically just a local variable. And then we ask, so did we just find a shorter path from the start vertex to the destination vertex? Well, I shouldn't say destination vertex, from the start vertex to vertex E, and that's because E is in the variable n in this case. And the answer is, yeah, we just found a shorter path, from the start vertex to vertex E, because the G value of E at this point is 17, and yet we found a path with a length of 13 to vertex E. So we go, okay, so we need to update a few things. So the first one to update is O, okay, but it's the same thing, E in here. And then the second thing to update would be the prev. So the prev of E is now no longer C, but D instead. And then we go back to change all the G and the F values. The G value is just whatever we have in variable t, which is 13 in this case. And then the F value is whatever the G value is plus the H value. And in this case, the H value from E to E is guaranteed to be 0. So it's 13 plus 0, and that's just 13 in this case. And that's it, right? This is the end of the for each loop. And then we go back to the while loop. So this time when we get back to the while loop, we only got one element in O, and we ask the same question. Okay, is there any element in O where its F value is less than the G value of the destination? Well, the destination turns out to be E also, right? So we are now really just comparing the F value against its own G value. The F value can never be less than the G value. And if you are just thinking, oh, okay, if text says so, then it is the case, then you might want to ask a second question, which is, are you sure, Tech? How do we know that? Okay, what makes you think that the F value of a vertex cannot be less than the G value of the same vertex? So let's pause here, okay? Because I'm trying to introduce what most people consider as critical thinking, because it's basically just asking a lot of questions, okay? You're asking a lot of questions, and you're not going to let go until you have a logical explanation, okay? So let's think about this a little bit. And the H value cannot be negative, okay? F, G, and H cannot be negative. Since the F value is the G value plus some H value, and none of them can go negative. They can be 0, but not negative. That is the reason, okay? So you guys are all correct in the text channel. Exactly. So without even looking, I can already tell that, hey, since the destination vertex is the only vertex left in set O, the condition that we need to stay in the loop is no longer true. So we are now exiting the while loop. So after we exit the while loop, we kind of construct a solution graph. So the solution graph is really just looking at the prefs of all of these vertices. Now A being the start vertex doesn't have a pref because just by definition, right? Because it's the start vertex. Why would we care? Where we need to come from for the start vertex? Because if we have a previous, that it by definition is not going to be the start vertex. So we look up. Okay, so who is remember, we have to track from the end. So we start with the destination vertex. The destination vertex is E, and it has a pref of D this time. And then the pref of D is C. And then the pref of C is B. And then the pref of B is A. So that's our shortest path. The shortest path is from A to B to C to D and then to E. Are we good so far about this trace? Any questions about this trace? Any specific row here that you might want me to go over again? I'll give you guys a little bit of time. All right, no further questions. Okay, cool. Anyone else? All right. How can we write down the answer? So the answer as the shortest path, or the answer as in the trace for the entire trace? This is the entire trace. The shortest path. So the shortest path goes from D, the destination. So we basically just track down from E, and then E has a pref of D, and then we look up D. D has a pref of C, and then C, D. So basically that's how we figure out the shortest path. I'm going to change the notes, because I want to only denote the shortest path. Because what we have here to define the graph, g of Sx, it is not wrong, but it will also include edges that really has nothing to do with the shortest path. So I'm just going to prune, all of the other edges and go like, yeah, you guys are not really that helpful. Yes, so the shortest path is just A, B, C, D, E in this case. Correct. That is correct. Alrighty. Alright, yeah, absolutely. Alright, so are we good? Alright, excellent. Any other questions related to Dijkstra's algorithm and the A star algorithm? Because if there are no questions about these two, we're going to move on to Predicate Calculus. I know it doesn't sound very exciting, but it's actually a lot of fun. Okay? Yeah. So what you guys can also do is to come up with your own graphs. Okay? Because when you just do when you're applying the algorithm to the graphs that I give you guys, you're just basically mechanically following the algorithm and just go like, okay, this is one step, this is one step. Is this condition true? If so, we're gonna do the conditional statement, then the then block of the conditional statement, and blah blah blah. So it can get very tedious. It's just kind of mechanical. But when you try to think of a graph and you ask the question of, now, how do we trick the A star algorithm? So it's going to go explore all of those pointless edges because they are not really on the shortest path. And I want to torture the A star algorithm as much as I possibly can. How do I construct a graph, and how do I assign the heuristic value to maximize the pain for the A star algorithm? That is the kind of thing that you might want to do in order to gain more insight into the algorithm. Now, to do that, you basically have to go through a lot of trial and errors, right? Because you basically create a graph, and then you follow the A star algorithm, and then you look at the actual outcome and go like, I thought this would trick the algorithm to explore these edges at least twice, but it did not. Okay, why did it not, right? So that's the question. If it did not do what you think that it would do, which is maximizing the pain level for the A star algorithm, then the question is, why didn't it do what you thought it would do? And that is really the process of understanding the algorithm, because as you think about these things, as you try to reason out all of these things, you are gaining an insight in the algorithm beyond the actual pseudocode, because those are the things that those are the connections in your mind that cannot be easily written in the notes that I give you. So thought exercises, okay? Thought exercises like that can help you. All right, so So without any further questions, I'm not seeing any questions in the text channel. We're going to move on. So we're going to move on to Predicate Calculus. Alright, so I think we can close the PDF here. There we go. And by the way, the PDF is from last Wednesday's text channel. So if you want to have a copy of the PDF, you just go to the text channel from last Wednesday. And I would just kind of stash all of these things into a particular notebook that you hopefully you have electronically. So this way, when you need to study and when you need to go back and rethink about something, you have a centralized repository of all of the material that you need. Alright, so we are now getting into Predicate Calculus. And Predicate Calculus can be extremely boring. Okay, and given that we only have, let's see, 15 minutes left, I'm not going to start with the boring stuff. Okay, we'll get back to the boring stuff. Okay, what is a substitution and so on. We're going to start with the fun stuff here. The boring stuff is really most of the definition stuff. Okay, so what we're going to do is we'll still kind of go through this note here because there are certain parts here that are actually just prologue stuff. So we're going to start with prologue. Okay, prologue is a very strange language. Back in the 80s, okay, so this is back to the 80s ish. The United States was competing with Japan in terms of AI research. Now, AI back then is not really the same as AI today. There are many different branches of artificial intelligence. So the artificial intelligence that I'm talking about is how do we reason? Okay, how do we think? How do we prove theorems? Okay, so it's the application of logic step by step. How do we deduce something? Okay, as opposed to what most people understand AI today is related to the application of neural nets. So I'm not saying one is better than the other one. They are simply different. Okay, one is more applicable when you have patterns that you want to recognize, but not necessarily understanding the mechanism. And the other one is all about the mechanism itself. Okay, so it's not about recognizing a pattern, but it is basically having a set of rules, and then you're trying to apply that set of rules in order to find something, in order to win a game, or something along that line. Okay, so that's kind of the backdrop of AI in the 80s. So people were doing a lot of symbolic processing. Okay, because if you want to parse a sentence, okay, if you are to give a computer an article to analyze, it's all symbolic processing. They're all basically just words, right? So there are two languages, that people used to process natural language and also to do deduction and stuff like that. One is Prolog. Prolog was the choice of not only Japan but also the Europeans. The United States or most American research institutions chose a language called Lisp, L-I-S-P, which is list processing. Okay, so those two languages basically were the main languages, the AI languages back in the 80s. Now, Lisp, interestingly, is still being used. Anyone who uses AutoCAD might actually notice that Lisp is the quote-unquote macro language behind AutoCAD, and it's kind of interesting, why they chose Lisp. Yes, Emacs also use a version of Lisp as its scripting language. And Lisp is a very interesting language because everything, guess what, is a list. Data looks like a list, and the program itself, it also looks like a bunch of lists. And it's a very nice setup to be a self-modifying program, because the program itself can change the definition of its own code. So what you start off as one definition of a function can change over time. The program can change itself. Yeah, weird language, but very interesting. So Prolog is the other one, and Prolog and Lisp are different in many ways. So let me see if I can still find a web-based SWI prologue. So SWI prologue, you can do a search engine and find it. Okay, SWI prologue, and they have a Swish. I like that name. Swish is a web-based interface to play with Prolog, and you can see I have a project here already. So it's kind of like online GDB. For those of you who program in C and C++, online GDB is a really good resource because you can actually write your code. There's a place for you to save your code, and then you can also debug it too. This is kind of online GDB, but it's not for C, C++. It's for Prolog. So let me start with something new so I can show you what it looks like. Okay, so let me see. Start together JS. No, that's JavaScript. Open recent. Alright, so how do I start it? Oh, there we go. That's kind of obvious. Create a program. Sure. There we go. Alright, so Prolog is a bunch of rules and facts. A fact is basically a rule that is always true. So let me, okay, we'll do it like this. Okay, so we'll say parent. Okay. And then we'll say, and we'll use lowercase and uppercase are actually significant in Prolog. Anything that has an uppercase is automatically quote unquote a variable, and anything that has a lowercase is not a variable. You can kind of look at those as constants. Okay, so they are not variables. They cannot change. All right. So if you want to make sure that the direction is known, you can say parent of, which means the first item is the parent of the second item. So we're gonna use The Simpsons. Okay. So Homer is a parent of Bart. Okay, and then we put a period here. This is now a fact. In other words, it is a rule, and it is the same thing as this. This is now a rule. So a rule is basically, it has a right-hand side and a left-hand side. This is the left-hand side, and this is the right-hand side. And it's basically an implication, but it's not what you think it is. It reads backwards. Okay, so the precedent of an implication is actually the right-hand side, and then the consequent of an implication is actually the left-hand side. So it reverses what we usually understand as an implication, and that part is kind of weird. But this is also just it's usually abbreviated as quote unquote a fact by not saying only if true, because to say only if true is sort of pointless. Okay. Yep. Exactly. So parent of Homer Bart must be true. So now you can enter a whole bunch of facts here, right? Homer is also a parent of, what is the second child? Lisa. There we go. What about the third child? The youngest one, the baby. Maggie, that's right. The genius. And then, obviously we also have Margie. So parent of, and then we got Margie. How do you spell Margie? M-A-R-G-I-E? Yeah, Marge. There we go. Marge. Okay, so Marge is a parent of Bart. Marge is a parent of Lisa. Marge is a parent of Maggie. There we go. Marge, Maggie. There we go. So now we have entered a bunch of facts. Who's the grandpa? Who's Homer's dad?
It's Abe, I think. Abe.
Yeah, I thought it's just Abe, but I wasn't quite sure. I haven't watched The Simpsons for a long time. So Abe is a parent of Homer. Okay, so now we can also enter, genders and stuff like that. So you basically just enter these facts, like, tiny little fragments of facts. So you go like, oh, that doesn't seem very interesting. This looks really kind of boring, actually. So now we can specify rules, okay? So what exactly is a rule? Well, we'll specify ancestor of, okay? Yes, that's one way to look at it. Very good. Okay, one way to look at this is it's a bunch of relations. Okay, but you can have many parameters here. So it's not really quite like relations that we talked about in this class, where you can only relate two items from the same set. Because now you can specify, like things with 3 items, things, facts with 4 items, and so on. So let's go ahead and specify a rule. So we say ancestor. I hope I spelled it correctly. And this time it is a rule because we're not going to use lowercase stuff. Okay, we're going to use uppercase stuff. So we now say x is an ancestor of y only if. Okay, now remember this symbol here, colon dash, is not if. It is only if, which means if you want to read this as an implication, it is the right hand side implies the left hand side. So now we go like, okay, what would be a good rule to use to determine that x is an ancestor of y? Oh, I know. If somebody is a parent of the other person, then technically it is also an ancestor. Okay, so parent of xy is going to be here. All right, so this is a rule. Okay, simple as it is a rule. Okay, because we are now saying if x is a parent of y, then x is an ancestor of y. Are we doing okay so far in terms of what is a fact versus what is a rule? Okay, so a fact basically is just a bunch of stuff like this with lowercase stuff, and then when we are talking about rules, now we are starting with, we are starting to talk about things with an uppercase thing, which is a variable. Okay. Yes, a rule is more general. That is correct. Because a rule doesn't quite say to whom we are referring to. Okay, so Homer, Bart, Lisa, Maggie, Marge, and Abe, those are called atoms in the entire universe. Basically, they are just things, okay, in existence in this universe, in the universe of this particular program. And they are concrete, okay? They're kind of like constants in C and C++. The rules, on the other hand, work with variables. So x and y are variables in this case. So now we can say, okay, what can we do about this? Okay, as it turns out, you can actually query this whole thing. So this is where predicate calculus and database queries are actually sort of related. Okay, they are not exactly the same thing. I'm not claiming they're exactly the same thing, but they are related. Okay, so because we can ask questions like this now. Actually, when we only have parent of, we can already ask those questions because you can ask something like this, parent of, and you can say, who is a parent of Bart? That is, what you enter here. And I think you need I think it's Control Shift Enter. Nope, Control Enter. There we go. So Control Enter says yes. So I just asked the computer, who is a parent of Bart? The computer came back and say true, which means there is at least one parent. Okay, Bart has at least one parent. So you might go like, who doesn't have a parent? Well, as it turns out, Abe does not have a parent here, because no rule, no fact here is going to say, this is a parent of Abe. So when we ask the same question here, and I think it's Shift Enter to, nope, it's Control Enter. Keep forgetting that. It says false, okay, because it says Abe does not have a parent. No one is a parent of Abe in this case. You can also do something different here. Nouns. Okay, so instead of an underscore, which is a legitimate variable, it's called an anonymous variable in this case. But now you can say, okay, let's not make it anonymous, make it x. Okay, and then we do the same thing, which is Control Enter. Now it would actually say, okay, it's the same thing because Abe does not actually have a parent. So let's go back to Bart. Control Enter. Now it says, okay, we have found that if Homer is X, then this fact holds. Okay, it is true. But you can also see there's a next button here. Basically, it's continuing to say who else is a parent of Bart. So you can actually query the system and say, if the constraint is we're trying to find parents of a particular atom or noun, give me all of those things that match. So from that perspective, this language is kind of weird, right? Because this feels like a database query. It feels like a select query, where you say, okay, one of the things of the table is fixed, okay, is a constant. That's where you specify the where clause in the select statement. But give me all the rows that matches, right? But we can do something that's even more interesting. Is older than, well, we don't know because the age is not entered here. There's no age information in as facts at this point, so we cannot even generate rules to make use of age to determine who's older than whom. It is entirely possible that a parent is actually younger than a child because of second marriage. So the technically, it would still be a parent of, because of the marriage to the other spouse, but it is possible for a spouse of a person to be actually younger than, at least one child from a previous marriage. So at this point, the ancestor thing doesn't do anything because anything parent of knows ancestor would come to the same conclusion. But then we're gonna do something that is fun, which is recursion. See, recursion is your friend. So now we're gonna say ancestor of xy, just like before. But this time we're going to say, what about Abe versus Bart? Okay, in this particular universe, Abe should be an ancestor of Bart. But yet, with only this rule, it's not going to be able to make that connection. So what are we going to do here? Y needs to be capitalized, yes, because it is a variable. Okay, so now we need to specify, oh, okay, so we can use, okay, this is where your understanding of relations actually comes in handy. This is transitive. This is transitive, okay? So we are trying to use the transitive property and say if x is an ancestor of z and z is a parent of y, then x is an ancestor of y, okay? But the order is important, okay? So it is important to determine which one comes first. So as it turns out, an ancestor needs to come first. So we say ancestor of, and this time we use z over here, okay? And somebody's going to complain and go like, but z is not even in on the left-hand side. Well, so that's there's a significance here, okay? And I'll talk about it, maybe later today. Oh, we're running out of time already, darn it. When you're having fun, time runs up really, really fast. Okay, but I'm going to finish this script first, and then we'll play with it. Okay, we'll now ask who is an ancestor of Bart. Okay, so we'll change parent of to ancestor of. There we go. Alright, so Control Enter will start the query. So it comes back with Homer. Okay, that's kind of, yeah, we kind of expect that, right? Let's find next. It finds March. Go like, yeah, we know that one too. And then we click next, and it finds Abe. Oh, now did you expect it to find Abe? Well, of course you did, because that's kind of the whole reason why I made this second rule. If I click next again, it's gonna say false. Actually, it will go into an infinite loop. So we're going to terminate the loop here. But you can see how we can make rules that are quote-unquote recursive in order to make things interesting. In fact, this, just like Lisp, Prolog has no concept of loops. There's no while, there's no for, there's no do. So how does it get iterations done? It's all recursion, okay? But it goes a little bit beyond recursion because it also has quote-unquote automatic backtracking. So we're going to talk about all of this on Wednesday, okay? And if you want to look it up, and because you just want to play with it, you can just go to the SWI Prolog website, and you can certainly use a switch, to kind of play around, because hey, this is the best way to learn how to use a Prolog. Yes, so all of these are basically base cases. But if you're talking about ancestor of, I think I messed up because the ordering is reversed. I think parent of needs to be the first one, and then ancestor of being the second one. Everything is user defined. So parent of is user defined, and so is ancestor of. So this is, it's not exact. This is one of the definitions of ancestor of, and this is the other definition of ancestor of, and they are evaluated in this order. So if this one fails, then we'll go to this one here and see if this one can give us an answer. So there's so this one is considered kind of the base case because it goes to this one first, and this one is the recursive case because it is it's only performed if the first one fails. Yes, kind of. So we'll talk about this on Wednesday. We are out of time today. And then Jonathan C has a question, like function overloading. It's not a function. These are rules. They are not functions. It has the kind of interesting thing about backtracking. Backtracking is basically going like, it finds a match here, but it cannot find a match here. Then it will go back here to see if there's another way to instantiate it so that this is satisfied again. It will try again with this one. So it automatically do quote-unquote exhaustive search, recursive exhaustive search, and it's built in automatic to the language itself. So that's why it can find all the possible answers without you actually having to specify the recursive nature and how to do the depth first search, which is basically what it does here. So I think this one needs to be reversed, and ancestor of zx, and I need to go back and change that one. X z and then zx zy. There we go. All right. Okay. All right. All right. So I'm gonna give this one more try, and then we'll end today's live cast. Okay. We find Homer, find Marge, find Abe, and then it terminates. So the order actually matters, right? Because I just reversed the order of these two, and it makes a difference, and it has to do with backtracking. So we'll talk about that on Wednesday. All right, so you guys take care. Start on the homework, okay? Because if you start on the homework and you go like, I'm not really quite sure what to do, we can talk about that on Wednesday too. All right, you're welcome. All right. I'm still online for the next hour because that's my office hour. So for those of you who want to kind of play with Prolog and ask questions, I'll be here. Yep, you too.